Hello students, in this video of Collegiate-Physics, you all are welcomed. In this video, we will present a short note on Zeeman Effect. Zeeman Effect is a magneto-optical phenomenon discovered in 1896 by Zeeman. When the source of line spectra is kept in a B field, the spectral line splits up into several line components. This effect is called the Zeeman effect. You know that when sodium atoms are kept into a discharge tube and high voltage is applied between the two electrodes, light is emitted whose spectrum contains line called D lines. When the sodium discharge tube is kept between the two pole pieces of an electromagnet and the current is allowed to pass through the coils of electromagnet, then a B field is established across the tube. In the presence of B field, again the spectrum is made of the sodium light emitted along the parallel direction of applied B field. In this situation, it is found that the original line is split up into two components. In transverse direction of B field, three components of spectral lines are observed. This effect is called Zeeman effect. Now, longitudinal Zeeman effect. If the splitting of spectral lines are observed along the parallel direction of the applied B field, then two spectral lines are observed. These spectral lines are circularly polarized. One is polarized in clockwise direction and the other is polarized in anti-clockwise direction. The frequency of one spectral line is greater than that of the original line by a fixed amount, and the frequency of the other line is smaller than the original line by the same fixed amount. This effect is called the longitudinal Zeeman effect. Now, transverse Zeeman effect. If the splitting of spectral lines are observed along the perpendicular direction of the applied B field, then the three spectral lines are observed. These spectral lines are plane polarized. The E vector of the central spectral line is parallel to the direction of the B field. Its frequency is equal to that of the original line. It is called the pi component. The other two components of the spectral lines are also plane polarized, in which the E vector of the spectral lines are perpendicular to the direction of the B field. The frequency of one spectral line is greater than that of the original line by a fixed amount, and the frequency of the other line is smaller than that of the original line by the same fixed amount. These components are called sigma components. This effect is called the transverse Zeeman effect. Now, normal Zeeman effect. We know that when a magnetic field is applied at the source of the spectral lines, then the line splits up into several components. These splitting depend upon the magnitude of the applied external magnetic field. There are two types of fields here. One is the internal field, which is produced due to the orbital motion and the spin motion of the electron moving around the nucleus. This magnetic field is of constant magnitude. The another magnetic field is the applied external magnetic field produced by an electromagnet. If the applied external magnetic field is greater than the internal magnetic field of the electron, then the splitting is normal. In a longitudinal direction of applied magnetic field, there are two components, and in the transverse direction of magnetic field, there are three components of spectral lines. This is called the normal Zeeman effect. Anomalous Zeeman effect. If the magnitude of the external magnetic field is reduced to a smaller value than that of the internal magnetic field produced by the orbital and the spin motion of the electron around the nucleus, then the splitting is very complex. It is called anomalous Zeeman effect. While explaining the anomalous Zeeman effect, we consider the effect of spin motion as well as the orbital motion of electron. But to analyze the normal Zeeman effect, we consider the effect of only the orbital motion of the electron. Paschen-Beck effect. If the external applied magnetic field is very large in comparison to the internal magnetic field produced due to the orbital and spin motion of the orbital electron, then the splitting becomes very simple in triplet form. This was discovered and explained by Paschen-Beck, so it is called the Paschen-Beck effect. A Stark effect. Stark studied the effect on the spectral lines when the source of a spectral